Today, what we will do is we will do this thing, module 4. So, what is this module 4? Frequency domain representation of LTI systems. So, specifically, both frequency domain representation of signals also and systems also we will try to do here. Okay, and especially for aperiodic signals. Okay, especially for aperiodic signals and those systems which will be processing aperiodic signals. Okay, so aperiodic signals can be continuous time or they can be discrete time. First we'll study the analysis of aperiodic signals in discrete time. For such thing we will have something called as discrete time Fourier transform. Okay, for such things we have something called as discrete time Fourier transform. Okay, so what is the formula for discrete time Fourier transform? You can see this here is the formula for discrete time Fourier transform. As I was telling yesterday, x of z was x of n z to the power minus n, right? It's also very similar. Only thing is z has been replaced by e to the power j omega. Z has been replaced by e to the power j omega. So what we are trying to do here is we are trying to represent x of n not with respect to the variable, right? Suppose you have this thing, right? X of n we usually represent with respect to n, right? N on the x-axis, x of n on the y-axis, or cos 2 pi omega n, sine omega n plus cos 4n, right? So that is usual representation as a variable with respect to the independent variable time. Here what we are trying to do is, here we are trying to represent x of n in terms of these coefficients, in terms of these coefficients, x e to the power j omega into e to the power j omega into, you can see this is a variable here, this is changing, right? See, j omega into 1, j omega into 2, j omega into 3, j omega into 4, and so on. So with respect to the fundamental frequency omega and its harmonics. Okay. So we are trying to represent, that is why the name frequency domain representation. We are trying to represent now x of n in terms of the fundamental frequency and its multiples. Okay, and its multiples. So earlier we saw something similar, right? That was Fourier series. Remember, Fourier series was existing for periodic signals and Fourier transform exists for aperiodic signals. Okay. So that one difference, let it be very clear. Okay, then you can see this is the expression for the Fourier transform. This is the expression for the Dtft, discrete time Fourier transform, and from this discrete time Fourier transform we get the representation x of n. Now what this the integration sign here indicates is, see, this summation sign, it indicated that my input x of n is discrete in nature. Okay, but whatever x e to the power j omega that I get from the process, that is going to be continuous, that is going to be continuous, that is represented by this sign, the integration sign. Okay, so even though x of n, the input to the Fourier transform is discrete, the discrete time Fourier transform is continuous in nature. Okay, so this particular discrete time Fourier transform is continuous in nature. That is one thing that I want you to remember. Second thing, you can see we are doing the integration from minus pi. Okay, let me write a minus here. We are doing the integration from minus pi to plus pi. We are doing the integration from minus pi to plus pi, and then we are dividing it by the period 1 by period 2 pi. That means x e to the power j omega is going to be, first thing first, it's going to be continuous. Second thing is x e to the power j omega is going to be periodic with period equal to 2 pi, from minus pi to pi, right? The discrete time Fourier transform is going to be periodic. Why I am telling you this is, we are studying two types of transform. One is the discrete time Fourier transform and another is the continuous time Fourier transform. The continuous time Fourier transform, whatever we learn, we will see, it will not be periodic. It will be aperiodic. Whereas the discrete time Fourier transform, whatever you see, this is going to be periodic with respect to period 2 pi. Okay. Let these things be clear. Okay, now does it exist by the way all the time? Now you might wonder and ask me that if at all the Fourier transform, if at all we could manage with Z transform, then why did we need the Fourier transform? Okay, see, the Z transform existed for the stability analysis and for the implementation purposes. The Fourier transform gives us the exact frequency behavior. It gives us the exact frequency behavior. Okay. So that is one thing. And second thing is Fourier transform actually does not exist for all aperiodic signals x of n. Okay, it exists only for this particular case where our x of n, the summation x of n, gives a finite quantity, or at least it's a square, or at least the square of a squared sum of x of n gives you a finite quantity. Otherwise, this x to the power j omega Dtft does not exist at all. This was not the case with your Z transform. Z transform existed for both unstable signals also and stable signals also. That was its advantage, but it could not do the frequency analysis. Now this thing here, Dtft, it can do the frequency analysis, but this does not exist unfortunately for unstable signals. Okay. That is a problem. Okay, now without wasting much time, let us get into a numerical. Okay, how does a typical numerical look like? Okay. So the problem here is, okay, let us get started. Okay. So here is a simple example, exponential. Okay. This one is the your normal the usual suspect. Right, alpha to the power n into u of n, a complex exponential. Now, does the Dtft exist for this, by the way? Does Dtft exist for this? It exists only if x of n is converging. If at all my alpha to the power n into u of n, say alpha is equal to 2, then it will be a growing exponential. For this particular case, the Dtft does not exist. Dtft exists only for the case magnitude alpha less than 1. Remember, okay, this is the difference. Okay, this will be the difference. Okay. So what we will do, by the way, yes, so we will assume only for this particular it exists. That is why you can see it's very specifically, it should be mentioned in the answer. Okay, so one thing is good that unlike your Z transform, Dtft does not come with this ROC and all. It's very straightforward. But then for checking, you should rightly mention, where does it exist, where it does not. Okay. So let us go and substitute. What is the formula for x to the power j omega n? So it is the same thing as Z transform. X of n e to the power minus j omega n, right? Z replaced by e to the power j omega. X of n e to the power minus j omega n. Okay, since this u of n is representing, u of n means existing only on the right side. That's why we have 0 to infinity. Okay, so what is the answer? We simply got this term here, 1 divided by. So as I said, exists only for magnitude alpha less than 1. That is why 1 divided by 1 by the term. Here actually your technically your answer ends here, but then we want to plot. Okay, sometimes the question will be like, plot the magnitude and phase response. To be able to do that on a calculator, this particular form is not a comfortable one. This particular form is not a comfortable one. That is why what we will do, is we will try to split this thing. We will try to split this thing and get it in a form that can be done on a calculator. Okay, we will try to get it in a form that can be done on a calculator, right? E to the power j theta on a calculator, I don't think so. That's why what we'll do is we'll split this thing. Okay, e to the power j omega is cos omega plus j sin omega. E to the power minus j omega, you can see the entire thing has been split here, entire thing is split here, and entire thing has been given in terms of magnitude, right? 1 minus alpha cos j omega plus alpha sin j omega it was. So the real terms combined and the imaginary terms combined, this will be the magnitude. Now this can be done on a calculator, right? Now this can be done on a calculator. Okay, then what about the phase angle? What is the formula for phase angle? minus tan inverse of imaginary part by real part. What is the imaginary part? Imaginary part is alpha sin omega minus tan inverse of imaginary part divided by the real part. So this should give you the phase angle. Now, how are you going to plot this thing? How are you going to plot this thing? So what we'll do is, if at all time permits, if at all you have a calculator, just because this is our first problem, what we'll do, let us see what will be the approach. We'll start substituting. We have to substitute here for omega, right? Because the y-axis is x of x to the power j omega, right? So that is what we have to do. We want to know the behavior with respect to omega. So what values of omega shall we substitute? We should start substitution from minus pi to plus pi. We should start substitution from minus pi to plus pi. Afterwards, the same pattern is going to repeat, right? Afterwards, as I told you, the Fourier transform, the discrete time Fourier transform is periodic with period from minus pi to plus pi. That is why it is going to repeat after from minus pi to plus pi. Same thing is going to repeat every 2 pi duration. Okay, so now what we'll do, we'll take the calculator. Just because it's our first problem, you don't have to do it actually. Okay, it will be there in the textbook, you just have to remember. Okay, so now shall we try? So what you are supposed to do is, you should take some points here. What we'll do is, we'll substitute omega equal to 0. What will happen if at all substitute omega equal to 0? Cos 0 is 1 only, so it will be 1 divided by root of alpha square plus 1 minus 2 into alpha. Okay, now depending on the value of alpha, if at all alpha is equal to 2, then remember Dtft does not exist at all. Okay, if at all alpha is equal to 0.9, 0.8, 0.7, 0.5 and all, what you are supposed to do is, you take this particular axis, then you simply calculate the value at alpha equal to minus pi and alpha equal to plus pi. It's going to be same, right? Then after other places, you will go on substituting. As you can see here, there is exponential term alpha square here. Exponential term alpha square here. Then compared to 2 alpha, alpha square is going to dominate, right? Compared to 2 alpha, alpha square is going to dominate. That's why your denominator is going to increase much faster with the value of alpha. Okay, and but at omega equals 0, maybe you will get a maximum value. Similarly, for the phase angle, what you are supposed to do, here also you will substitute for minus pi to plus pi, right? Why I'm telling this is, sometimes you don't know, what is the expected shape in exam. You can just take your calculator and you can make a wild guess, maybe, by substituting a few values. Okay, you can see here in this particular format, there was no way for you to substitute it and get a value on the calculator. That is why this format, the one with the magnitude and phase straight away. Okay, let us see. Let us cut the crap and let's move to check how actually it looks like. Okay, here. Okay, so here we see, you can see here, this is the value from minus pi to plus pi. There afterwards, the same pattern just keeps repeating. Okay, so you can see it's a bell shaped one. As I told you, there was an alpha square in the denominator, and compared to 2 alpha, and this with a minus sign here, alpha square dominated. So as and when the values increased, on the positive side, as the values increase on the positive side, well, one thing, it was depending on alpha, right? Not on omega. But what we are changing, what is this axis? This axis is my omega. Okay, so yeah, it's on the behavior of omega. Sorry. Okay, cos 0 omega is maximum, right? But as and when omega increases, the cos value goes on decreasing, right? The cos value goes on decreasing. How much maximum it can go, by the way? It can go on little from minus pi to pi. That's what happened. As expected, the cos value went on increasing and bringing this entire thing down on either sides. And this here is the expression for the phase response. This here is the expression for the phase response from here to here. So here to here. Okay, this expression. What will be the value here? What will be this value here? Tip at omega equal to 0. At omega equal to 0. So shall we substitute? omega equal to 0, this author says is the value for, he has assumed a value of alpha here. Alpha, the author here has a, has taken what happened screen. One second. One second. Okay. Sorry for that. Okay. Yeah. So we are back. Okay. So what is it by the way? So the problem has ended actually earlier. We are just trying to do a plot here. As I was telling, we are trying to do the plot of the answer. So what was it? At omega equal to 0, what do we get? Alpha here is assumed to be 0.5. You can see this is a graph where alpha is equal to 0.5. So 1 divided by 0.5 square plus 1 minus 2 into 0.5. Okay, so what will be that by the way? What will be that? Cos omega equal to 0 anyway. Cos omega equal to 1 anyway. So at omega equal to 0, we will get 2. Do we get 2? Do we get 2? Hmm? So substitute omega equal to 0.5. Alpha is equal to 0.5 whole square is 0.25 plus 1. Okay, 0.25 plus 1.25 minus 2 into 0.5. 2 into 1 by 2. 2 into 1 by 2 is what? 1. 2 into 1 by 2 is 1. Then a whole root. Then a whole root. And what is the magnitude here at the center? Magnitude they are telling it as 0. Okay. So maybe this is the answer. Can anybody just check and tell me if at all I substitute omega equal to 0 and alpha is equal to 0.5, what do I get? 0.5, what do I get? This is 0.25, right? 0.5 square, 0.25 plus 1 minus this one. Okay, minus 1. 1 minus 1. These two will be gone. 0.25 whole square under 0.25. 1 divided by 0.5 is equal to 2. Yes. Yeah, maybe this is correct. So basically what you are supposed to do is just remember the shape. Remember the shape for a complex exponential. Alpha to the power n. Alpha can be 0.5, alpha can be 0.2, or alpha can be 0.9. Okay. So you just have to substitute the value at the 0, then maintain this particular shape. Okay. So we cannot keep on calculating the values all the time. Okay. So what is the conclusion of this whole story? Dtft. Okay. So our answer was technically, it ended here. Our answer had ended here, but then we wanted to plot the magnitude and phase. That is why we went a step ahead. Split them in terms of real and imaginary parts, then got the magnitude and phase angle. Okay, then got the magnitude and phase angle, and we found out that the thing is periodic. The thing is periodic from minus pi to pi. Afterward, the same thing keeps on repeating. Afterwards, the same thing keeps on repeating. Okay, remember that. Now let us see one more example. So first example what we saw was that of a complex exponential. One more usual suspect is a rectangular pulse. Okay, one more usual suspect is a rectangular pulse. So this is discrete time. So when author means a rectangular pulse, he means this is being a one, from so many at certain point, continuous ones. Okay, this is what author means for a rectangular pulse. Okay, this is what author means for a rectangular pulse. You can see x of n is equal to 1 for certain, minus m to plus m, maybe from minus 5 to plus 5. Maybe from minus 5 to plus 5. It is all one. Discrete time signal. So we want to find the Fourier transform. Okay. So we want to find the discrete time Fourier transform. So definitely a periodic signal, right? Definitely a periodic signal. So what will substitute here? What will substitute? So 1 for magnitude minus m to plus m. So we'll substitute in the formula. We'll substitute in the formula. Now you can see whenever we are changing, yes, from minus m to plus m. But we are comfortable with those limits which will go from 0 to some positive value. That is why the change in the limits. That is why the change in the limits, and you get in this particular format. 0 to n of a to the power n. 1 minus a to the power n plus 1 divided by 1 minus a form. There we substituted. Okay. There we substitute format, and we got this particular thing here. and you got this particular answer. There is a small problem here in this particular answer. This was easy, right? So what did we do? From this 0 to n, of 0 to n became n plus 1, 1 minus a. Okay, that was a direct substitution. But then for omega equal to 0, you can see, if at all I substitute, denominator is 0, numerator also goes to 0, which will give me indeterminate form. That is why author mentioned here, this exists only for omega equal to 0, 2 pi, 4 pi, and so on, right? For omega equal to 0, this was giving me a 0 divided by 0 form. See, this is the tricky part. Okay, that is why what you have to do. For omega equal to 0 case, what we will do, we will compute the entire thing at the first summation only, right? Here itself or here, right? Here what happens is, the moment I substitute omega equal to 0 here, it simply becomes summation from 0 to 2m, summation from 0 to 2m of e to the power 0, 1. What will be summation 0 from 0 to 2m of 1? So it will be whatever the value plus 1, right? Isn't it? Are you comfortable with this? Summation 1 from 0 to 4 is what? 1 to the power 0 plus 1 to the power 1 plus 1 to the power 2 plus 1 to the power 3 plus 1 to the power 4. How much it will be? It will be 4 plus 1, right? I think we know this. Know this. So similarly, for the case of omega equal to 0, 2 pi, and all those places where we would have got an indeterminate answer, 0 divided by 0, we will do the substitution here itself in the beginning. So we'll get summation 1 from summation 0 to 2m of 1, which will give us straight away the answer 2m plus 1. Okay, it will give the answer 2m plus 1. Now here also we are sort of interested. Okay, our answer technically has ended here, but this thing does not let us plot the magnitude and phase response. Okay, this thing also does not let us plot the magnitude and phase response. That is why what we have to do, once again here, we have to go for splitting this thing. How are you going to do it? Is there is a specific thing, by the way. Okay, so whenever we say a rectangular pulse, we want to represent the DTFT in a form of sine divided by sine for a specific reason, which will be clear when we see the answer. Here you see what author has done here is, so this has got not much of a logic, but only with the familiarity we can know. Okay, so he took this particular term outside because author wanted to represent it in the form e to the power j theta minus e to the power minus j theta by divided by 2j, both in the numerator and denominator. So to be able to do that, to get same terms here on the power, he had to take this particular term outside. Okay, now you can see here he got e to the power minus j omega 2m plus 1 divided by 2, e to the power j theta minus e to the power minus j theta. 2j anyway will get cancelled for both the cases. Hence he got it in the form sine divided by sine. Okay, he got it in this particular form. It's a sine wave dividing by something which is once again also periodic in nature. Okay, you got this particular thing, something that is sinusoidal, which gets divided by something which is once again sinusoidal, and there are exceptions at 0. Okay, see the way it has been rewritten. So what that does, by the way, this kind of style results in something like this. It is going to result to me something like this. You can see sine divided by sine at omega equal to 0, we had 2m plus 1, right? At 0, at 2 pi, at minus 2 pi, we are not bothered, right? We are bothered only from minus pi to plus pi. We are bothered only from minus pi to plus pi. By the way, why there is only magnitude in earlier problem? We had both magnitude and phase. Remember, in the earlier problem what we saw, we had both magnitude and phase, right? See here, we had magnitude and phase. We plotted magnitude and phase response. But in this particular problem, you can see our answer is purely real. Our answer x to the power j omega is purely real. That is why we need not plot the magnitude and phase. Okay. So what is it, by the way? So you can see the shape of this particular signal is of interest. Okay, from minus pi to plus pi, the thing afterward the thing repeats. Okay, at omega equal to 0 you get a maximum peak of 2m plus 1. This is very difficult for us to predict. Okay, I urge you all to remember this particular value, but you can see the shape of this. The shape of this is a sort of this kind of bell shape which is going on decreasing. It is like a sine wave only which goes on decreasing. Why that happened? It was a sine wave, but below that was one more sine wave which kept on decaying this value, right? Which kept on decaying this particular value, so it could not sustain the amplitude, but it went on decaying, and we got this particular wave. This particular wave is called as a sync wave. This particular wave is called as a sync wave. Okay, a sinusoidal wave whose shape goes on decreasing, whose shape goes on decreasing. Okay, this is of an interest to us because it will be convinced when you see the next numerical. Okay, so you'll be convinced in the next numerical. So what is the conclusion of the story? The conclusion of the story is the dtft of a rectangular pulse is like a sink. Dtft of a rectangular pulse is a sink. Okay, as of now. Now let us see the next numerical. Now let us see next numerical. So all these numericals here, we are just trying to make a point, and we are trying to understand the DTFT behavior and the dual behavior between the DTFT and the time domain. Okay. Now you can see we are trying to do something different. Here, earlier we saw the DTFT of a rectangular pulse was a sink. Here for a change, we will try to find a sink, a rectangular pulse in the frequency domain. Okay, this is a rectangular pulse in the frequency domain, right? Are you convinced that this is frequency? Minus pi to pi. This is the frequency domain. He wants to identify what is, he has given x to the power j omega. He wants to know what is x of n here. He has given x to the power j omega, and he wants us to know what is, wants us to find out what is x of n here. So how do we do this thing, by the way? How do we do this? You start with the formula. You start with the formula. See, author had given us the expression, okay, not the figure. Author said that x to the power j omega is 1 for magnitude omega less than some w. Okay, and 0 for this w from w to pi. Okay, since the magnitude sign was there, it meant that it will be 0 from w to pi and minus w to minus pi. Okay, that's what the author actually meant. Okay, you got this thing. So if at all you are given the figure, you are lucky. If at all the expression is given, from going from expression to figure is the tricky part. Okay, going from expression to figure will be the tricky part. Okay. Okay, so now how do we do this thing, by the way? This is the expression. You remember, this is the expression for the inverse DTFT. Okay, the expression for DTFT was that similar to your Z transform. X of n e to the power x of n z to the power minus n. This is the expression for IDTFT. Okay, so 1 divided by 2 pi, the period. This will be constant. The period is always 1 by 2 pi only. So we will not take from minus pi to pi, because from minus pi to minus omega, this is anyway 0. And from omega to pi also, this is anyway 0. So what is the actual expression for IDTFT? The actual expression for IDTFT is here. See, this is the expression for actual IDTFT, minus sign, sorry. Okay. This is the expression for actual IDTFT. From minus pi to pi, we will take only the values where it is non-zero. That is why what we have here is minus omega to omega. Okay, we'll call it as w. Minus w to w e to the power j omega n. Okay. What is this e to the power j omega n? Is actually 1. E to the power j omega n is the part of my expression. Okay, e to the power j omega n is part of my expression. The value from minus w to w is simply 1. We will simply find the inverse. We will simply find the inverse here. And what would I have got, by the way? So this would be something like e to the power jw e to the power jwn minus e to the power minus jwn. 2j is here, divided by 2 and j is here. So e to the power j theta minus e to the power minus j theta divided by 2j is nothing but sine theta. So that is why we'll get sine omega n divided by pi n. Once again here, for n is equal to 0 at origin, sine 0 is 0, pi into n, pi into 0 is 0. So this will give you indeterminate format. So for n is equal to 0, again you will substitute here. So what do you get here? E to the power 0, 1. Okay. So w minus minus w, that will be 2w divided by 2 pi. So it is w divided by pi. Okay, so at 0, so the shape of this thing, so this is also a sine wave, this is also a sine wave, except for 0. So at 0 this is w by pi only. Then afterwards, as and when the sine wave kept on increasing, there was a denominator. As that sine wave maintained its amplitude, the denominator which went on increasing, that is why the entire thing kept on decaying. As you can see, what sort of wave is this? This is something similar to what we got in the previous numerical. Okay, a sync wave. Okay, this is similar to what we got in the previous numerical, a sync wave. So what author wanted us to know is the dual property between time domain and the frequency domain. What was that? The Dtft of a rectangular pulse, is a sync pulse, and Dtft of a sync pulse and Dtft of a sync. See here, this is the time domain thing, right? Dtft of a rectangular pulse is a sync. Dtft of a sync pulse is rectangle. Okay, this is one thing which author wanted us to know. That is why he did this, right? Answer was simple, but he made this thing in this particular format. Okay, and once again, tricky question. See, whenever there will be several numericals where you get this indeterminate form for a particular value of n. Such cases, what you have to do, we try to substitute in the first expression itself, or otherwise author says for smaller values of n, sine of n would be n itself. That also can be substituted. So for smaller values, n tends to 0, sine omega n will be omega n only. So that's when you can substitute that and you can still get this answer. Okay, one more thing. So super. Now let us see one more standard problem and let me stop today. Okay. So what is this thing, by the way? This is an impulse. Okay. X of n equal to delta n. So what is the Dtft of this? What is the Dtft of this? X of n is equal to delta n will have a Dtft of 1. Okay. So how did this happen? X to the power j omega, x of n e to the power j omega n. Now since delta n exists only at 0, we will simply substitute where its value is 1. In place of delta n, we will substitute 1 and e to the power 0. E to the power 0. No summation needed. There is only one value, right? So it is, the answer given as 1. Okay. Answer is similarly, if Dtft of delta n is 1, Dtft of delta n is 1, IDTFT of delta omega, we will see, will also be a constant, is equal to 2 pi. Okay. What is the meaning of this thing, by the way? So IDTFT of delta and delta omega. So this is 1. IDTFT of delta omega we will see tomorrow. Okay, I'm going to stop today. IDTFT of delta omega is going to be 1. So that means an impulse in the time domain is a what? Impulse in the time domain is a constant in the frequency. A constant in the time domain is an impulse in frequency. Okay, there will be a constant 1 by 2 pi also here. Okay, there will be a constant 1 by 2 pi also here. We will see this particular thing tomorrow. Okay. So that was that introductory class on the discrete time Fourier transform. Tomorrow we'll see a few more numericals, and then we will straight away go to the properties of Dtft. By the way, did you observe the similarity between the Dtft, right? And was Z transform, was it periodic? What was the nature of Z transform? Z transform, by the way, you might remember, Z transform also existed for discrete time signals. What was the nature of Z transform? What was the nature of the, do you remember the Laplace transform? Laplace transform exists for continuous time signals, whereas the Laplace transform is whether it is continuous or discrete. You have to check and tell me. What about this x to the power j omega? Was it continuous or discrete? X to the power j omega is continuous. X to the power j omega is periodic with respect to period 2 pi. What about x of z, by the way? What about x of z? You might remember, how did we represent Z transform? All the Z transform were represented in terms of circle, right? Alpha to the power n of n. What was the Z transform? Z transform was a circle. Remember? Let me draw a neat one. Okay. Yeah, I'm getting. Huh. Yeah. Z transform was a circle. That means you start from here, you go all the way by 360 degrees, and then afterwards, if at all you continue, once again the same thing keeps on repeating, right? The same thing keeps on repeating every 360 degrees. So your Z transform was periodic in nature. Z transform existed for aperiodic signals, but Z transform, you could see, it simply rotates around the circle, right? Simply rotates around. So it was periodic with respect to period 360 degrees, right? It was periodic with respect to period 360 degrees. That is why the expression for inverse Z transform had a circle. Remember, we did not calculate the inverse with that formula, but it was, what it meant was, you are supposed to perform integration over the circumference of the circle. That's what it actually meant. Okay. So similarly, okay, so yeah, that's that. Okay, so we'll stop here today. Tomorrow we'll continue with more number of problems. Today we are just trying to make a point of the properties of Dtft and its similarity with Z transform and its very nature and the duality. Tomorrow we'll get started with all the numericals and problems based on the properties. Okay. Okay then. Thank you. We'll meet tomorrow.